Okay, this is the thermodynamics practice problems worksheet for advanced chemistry. This is basically a summary of what we've been learning about. And we'll also show one additional type of problem that you might encounter. The first problem, though, is one we looked at many times before. And the problem simply states that two samples of water are combined. So we have two containers of water. One sample has a mass of 85 grams and an initial temperature of 45.0 degrees C. The second sample has a mass of 45.7 grams and an initial temperature of 87.0 degrees C. What is the final temperature of the mixture? The specific heat of water is 4.18 joules per gram per degree C. Okay, so we know this is the more hot solution. This is at 87.0 degrees C. This is the cooler solution at 45.0 degrees C. We're going to mix the two. And we'll have a total mass of the solution, and we will have some kind of final temperature after the two waters mix, the two samples of water mix. We know that heat will flow from the 87 degree water to the 45 degree water, and we'll achieve thermal equilibrium. So what we're looking for is the final temperature. Now, just to go back and label these things, we're going to use that idea that heat or energy lost plus heat or energy gained must equal 0 due to the conservation of energy. Okay, at this point we're going to skip ahead a couple of slides to a blank slide, and we will continue the calculation there. It takes quite a bit of space. Okay, for the next problem, number 2, we're calculating the change in the standard entropy for the reaction that's given, where 2 potassium chlorides react with 3 moles of oxygen to produce 2 moles of potassium chlorate right here. There is a data table on the back page, data on back sheet. Okay, so in order to do some kind of problem like this, you have to be given the data. So if you look at the data, you'll see that you've been given the standard entropies, and those will be used in the summation equation to calculate the change in entropy for this reaction. So first thing, write out your general formula for this. So again, S stands for entropy. The little naught sign means standard, and then RXN means for this reaction. So again, it's going to be the summation of the entropy change for the products minus the summation of the entropy change for the reactants. Okay, and now we're going to, and this is the approach I would use, Don't worry too much about the not signs and all that sort of thing. There are a lot to remember at this point. So we're going to do 2 big sets of brackets. And we're going to do the products minus the reactants. So first of all, potassium chlorate is the only product. We see that we get 2 moles of potassium chlorate produced. So we are going to do 2 moles. We will look up the value for the entropy of potassium chlorate. That comes out to be 142.97 joules per mole Kelvin. Remember, the units for entropy are joules per mole per Kelvin, so you've always got to check and make sure your units are consistent. From a data table, you get the right units. Minus, now the reactants, potassium chloride's a reactant, you looked that up, so there are 2 moles of it, so it's 82.68 joules per mole Kelvin. And we have 3 moles of oxygen, and that is 205.0. Again, joules per mole Kelvin. Okay, so we've got everything in place and organized. Recall that we have 2 moles of potassium chloride, so we multiply by 2. 3 moles for the oxygen, 2 moles of the product potassium chlorate. Okay, that becomes a matter of doing the math. Just watch your signs. And now this all comes out to be minus 780.36 joules per mole Kelvin. And if you go ahead, finally calculate out the value, it's a minus 494.42 joules per mole Kelvin. And if you go back and look at our data, let's see, 5 sig figs, 4 sig figs, 4 sig figs. So probably we could stick with 4 sig figs. So we would go to minus 494.4 joules mole Kelvin. Okay, so in taking a look at this, you want to ask yourself, does it make sense that the entropy decreased in this reaction? And this is where having the phases identified for the reactants and products is very important. If you go back and look at potassium chloride, it's a solid, so very little entropy in a solid. It is, however, reacting with 3 moles of oxygen gas. Gas has a very high entropy. So those two combined produce 2 moles of solid. So most definitely the entropy is decreasing because you're losing gas. So entropy is definitely decreasing. So our answer with a negative sign is very consistent with what is actually happening in the reaction. So the last question for this asks us to describe the change in disorder for the reaction above. Explain your answer. So we just said that we had two moles of solid reacting with 3 moles of a gas, and in the end 2 moles of solid was produced. So we've lost a tremendous amount of entropy because our gas is no longer there. And so the entropy, as we said above, the entropy the entropy decreases since gases are combined to make solid. And you might also say solids have much less disorder than gases. Okay, that should take care of answering the final part of this question. And the question number 1, well, okay, so for this problem, this is actually the last type of problem we're going to look at. It's a variation on the delta G equation. And what we know is this, if we look at this as a free energy curve, which means it's the potential for doing work or making energy. Delta G is less than 0 on this part of the curve, so it would be going in the forward direction. Delta G is equal to 0 at the very bottom. The system is in equilibrium. And then the delta G is greater than 0 on the other side of this. So this is one way you can remember this. Anyway, so in this case, we say the reaction is spontaneous. At delta G, the system's at equilibrium, so it's not changing at all. And at delta G greater than 0, then we know it's non-spontaneous. So what we do know then is that there is a point, and it turns out to be temperature. There is a temperature at which the spontaneity changes. It has to pass through 0. So the way we figure out what that temperature is, if we're given the enthalpy of the reaction and the entropy, we can use the delta G equal delta H minus T delta S equation. If we are given, in this case, we are given the delta H value, the delta S value, and what we know is that when the spontaneity changes from negative to positive, it must pass through 0. So in this case, we're going to set delta G equal to 0. So delta H minus T delta S. T equals delta H over delta S. And we're given those values, so we can substitute those numbers in. The enthalpy of reaction is 176.79 kilojoules. The entropy for the system is 285.44. Well, this will be kilojoules per mole. This will be joules per mole Kelvin. And again, this is in joules, this is in kilojoules, so you have to make the change to convert to consistent units. So we'll convert to kilojoules. So we're going to divide, you need a factor here. 1,000 joules is 1 kilojoule. So now if you look at this equation and you calculate or you check your units, moles will cancel, joules will cancel, kilojoules cancel, and what you're left with is Kelvin right here. And those are the appropriate units for temperature. So now we have to do is do the math. And we come out with 619.4 Kelvin. Let's see, we have 5 sig figs. Actually, the temperature. Oh, well, the temperature is what we're looking for. So we had 5 sig figs. So we could even have one more here. Not sure what that would be. I don't have it down here. Anyway, so at this temperature, a temperature of 619.4 Kelvin, the spontaneity of this reaction is going to change. So this is the turning point. For spontaneity. And if you want to check to see how this affects it, pick a temperature of 200, substitute in, see what delta G is, and then pick a temperature, say, of 1,000. Go ahead, put that into your equation and see what delta G is, and you should see that the spontaneity of the reaction changes when you go from something below 619.4 to something above 619.4. All right, so you should know how to do this, and that's pretty much it for the calculations in this particular unit. Definitely want to know how to do this question here. I guess it's actually on. Okay, so we're on thermo problem number 1. Okay, so we're going to use the MSHAT formula. Q equals M SH delta T. We'll start writing out our variables. So 45.7 grams of water. The specific heat of water is 4.18 joules per gram degrees C. We have T final minus T initial, which was 87.0 degrees C. And that will be added to 85.0 grams of water times 4.18 joules gram degrees C. And the final factor T final minus 45 degrees C. So these are all T final. This was a T initial for the warm sample. This was T initial for the cold sample. Those two added together must be equal to 0. Okay, so now this is where you really just have to pay attention to the math. Be very careful about the math. So we have 191.026 joules per degree C times TF minus 87 plus 355.3 joules per degree C times TF minus 45 degrees C equals 0. Go ahead, continue doing the algebra. Eventually you come down to the point where you're combining the F terms, carrying a lot of extra decimal places. We'll look at sig figs at the end. So here's where I've combined the T final term, minus 32607.762 equal to 0. Finally, TF equals 59.69. If you go back to the original data, most of the data has 3 significant digits. So we will round this to 3. So we'll have an answer of T final equals 59.7 degrees C. And there you have it. This is the easiest way to do this kind of problem. You'll see other arrangements where the heat lost equal the heat gained. And those, in using that approach, you have to pay very close attention to getting the math right. This is actually easier mathematically than some of the other approaches to doing this problem. Okay, well, I hope that's an example of something you should be able to do. This page right here, question page 3, it's the adding hot to cold, so you definitely want to know how to do that one as well. All right, that's pretty much it. Take a look at this. This will be helpful on the exam, on the part 2 of the exam on Friday. All right, thank you. Okay, now this question is actually number 3. It is not on the worksheet, but it is on the answer key. So something got lost in the translation. So this is number 3. And we have, this is the reaction to nitrogen dioxide gas. That's what they call an equilibrium. Goes to N2O4 gas. Again, data. You're going to look at the data to see what kind of equations you might use for this. The data is on the back of the sheet, and given what kind of data we have, we again are going to use the summation equation. So the delta H, so the standard comes from the naught. H means enthalpy, so the standard enthalpy change for this reaction is going to be the summation of the enthalpy standard enthalpy of formation of products minus the summation of the delta H standard enthalpy of formation of reactants. So we're going to substitute in all those numbers. Actually, in this question, which we don't actually have before us, they're telling us that the enthalpy, standard enthalpy change for the reaction is minus 58.0 kilojoules per mole. And we're asked to find the delta H of formation of N2O4. So that's the product. And again, we're just setting this up the same way we've done before. Minus 2 times 33.85 kilojoules per mole. So we are actually given the value for the enthalpy of the reaction. We are looking for the enthalpy of formation of dinitrogen tetroxide right here. And we were given the enthalpy of formation for nitrogen dioxide. So setup is the same. Big parentheses for everything to include the products first, then big parentheses to include everything for the reactants next. Okay, so now it's just a matter of solving the math. So the enthalpy of formation of NO2 is going to be equal to minus 58.0 kilojoules per mole plus 2 times 33.85 kilojoules per mole. And now we're going to go ahead. Everything's in consistent units, kilojoules per mole, so this is good. These are kilojoules, these are kilojoules. And in the end, we come out with the enthalpy, standard enthalpy of formation for NO2, for N2O4 is minus 58.0 plus 67.70, again, kilojoules per mole. Final answer, the enthalpy of formation for N2O4 equals 9.70 kilojoules per mole. And sig fig wise, the data had 3, 4, could go with 3. And to talk a little bit about this question, the question is about the whether the reaction is endo or exothermic. We were given the data for the reaction, the enthalpy of the reaction initially, and that was minus 58.0 kilojoules per mole. And the negative sign indicates that this is an exothermic reaction, which means energy was released, which means that the products are at a lower energy level than the reactants. Okay, so this is again another very similar to what we did many of in the PowerPoint video. Okay, so this is also an additional problem from what's on the sheet is number 4. We are combusting methane So we have carbon dioxide as a product. And of course, these are all gases. And the temperature of the reaction is at 275 Kelvin. And the other information we're given is that the enthalpy change for the reaction is minus 891 kilojoules per mole. That the entropy change for the reaction is minus 243 joules per mole Kelvin. And the question is, what is the delta G value for this reaction? Well, there's two big things that you have to pay attention to when you're working this problem. First of all, we're going to write the equation. So delta G equals delta H minus T delta S. So the delta H term and the delta S term both have units for energy, but they are not consistent. So we're going to have to make consistent energy units. You can do kilojoules to joules or joules to kilojoules, doesn't matter. And your temperature must be in Kelvin when you're using this formula. So those are the first two things to check. And then now you go ahead and substitute into the equation. So delta G equals minus 891, here let's put a decimal place here, kilojoules per mole, minus 275 Kelvin, minus 243 joule Kelvin. And we're going to convert joules to kilojoules, so 1,000 joules is equivalent to 1 kilojoule. These joules will cancel. These K's will cancel. Oh, and this is joules per mole Kelvin. And so in the end, you'll have kilojoules per mole left as units on this part of the equation, and they'll be perfectly consistent with units on that side of the equation. So now all we have to do is go ahead and do the math. Minus 891 kilojoules per mole minus 66.83 kilojoules per mole. Finally, delta G comes out to be minus 957.83 kilojoules per mole. We have about 3 sig figs in our data, so we'll round to 3 sig figs, which means the answer for this will be 958 kilojoules per mole. Okay, and the fact that this is, oops, let's take a look. I left off the minus sign when I went from this to boxing in my answer, so minus 958 kilojoules per mole. Delta G is negative. This, you need to know the signs for delta G. If delta G is negative, delta G equal or is less than 0, in other words, it's negative, then the reaction is spontaneous. So the reaction will be spontaneous because delta G is negative.